capacity when they're not even on. And it could take 2 hours to get them hooked up and running. So it's, and some of them are spinning and can go on instantly. So it's a very abstract setup. So the area under this curve is what the loss of load probability is. The area of under the entire thing is 1. It's the probability density, and they go and compute that, and they set that equal to 1 blackout every 10 years, and and that's how they get the reserves, and you get 12%. But this term is used all the time, even though I do claim it's impossible. It just, there's no way to make sense of it. And so, so the homework, I was asking you to play with this. I didn't all I wanted you to do is simulate. But basically, if you have a cost function, I feel a little more comfortable with all this. Doesn't seem quite as arbitrary. It's hard to define these things, as I mentioned last time. Having a linear cost of shedding load, of course, as I said, you would all agree is ridiculous. Different uses of power have different preferences. And so a great example is Alcoa, who today participates with big ISOs and shuts down their operations or slows down their operations if there's a problem. And so their value of power is not, their marginal value of power is much lower than Shan's, as I pointed out. So again, this would probably be a very smooth convex curve on the left and not this linear curve in real life. But in the literature, you'd see linear curves like this. And even not just academic, but power systems people talk about the value of lost load as if it's a single number, even though they know it's not true. And this thing here, this abstract thing of the cost of extra reserves, it's also very abstract. It's, if it's a generator that's spinning, it's actually using power. If it's a generator in Northern California, it's an opportunity cost. Here I am promising to supply power to California ISO when I could be supplying power for real to Oregon. So this is a very abstract thing as well. It'll be very hard to pin down. But if you can formulate something, at least you get some intuition. If you can get some approximation of what this cost should look like. And then there's 2 ways to think about this. So, all right, we got quorum now. So why did I do this? So if I've got a cost function and I get to choose my reserves, why wouldn't I minimize this? The only reason for this is because for historical reasons. So God, what a horrible alphabet soup. So the expected energy not served. Oh, wait. It's that's not true. Sorry. And that's still wrong. I'm sorry. Expected. Hold on. Expected, and that's getting myself confused. There we go. So the expected energy not served. Oh, I don't have to flip that. I'm putting a cost function in. I was worried this would happen. I took the red eye in. I got 3 hours of sleep. So I'm going to make some mistakes in this lecture. Sorry. It'll slow me down.
Is that G minus D when G is greater than D? Expected energy not served?
Well, yeah. So I'm integrating from minus infinity to D naught. So and so I'm always looking at. I'm not meeting. This is how much load I'm shedding. So I could really. This is just equal to D naught minus G, because I'm always looking at G less than D naught. Okay. So So this is a standard metric that's used in evaluating power systems and all, which makes a lot of sense. And this is just and this is what you would set equal to a target. You know, and I like this a lot better than the probability, the probability of lost load, because it tells you, it's has much more information in it. But of course, the mistake I made was basically multiplying by that constant there, which is what's part of this cost function. You know, so the thing I'm looking at, this expectation here, is looks like this. It's going to be one integral up to here, what I wrote down. That's the first term. So I've got just a linear function with this slope minus value of lost load, and which is hits 0 here at d naught at this forecast, the actual demand, a forecast demand, and then it's got this other thing. So this is a refinement of the standard expected energy not served. So these are really 3 different metrics we're talking about. Now, you can't minimize this because you'd end up saying the reserve is equal to infinity. You basically shift that histogram so that you never ever saw a problem. With this, you can go and think about optimization. And a target doesn't make quite as much sense. All right. Okay. And so that's that.
So this is summation of 2 integers, right?
There's a big summation sign here. That's right. So given this cost function, that's what you get for the. That's one way of writing it down.
So vol stands for the shedding.
What's that? The value of lost load. How?
C R is the value of.
Yeah.
C R is the value of.
Or the cost of keeping extra reserves. Yeah, that's right. Yeah. All right. Now, yeah, that's right. So this might be a reasonable assumption that if you have more reserves, you just shift that histogram about. But as I said last time, it's not completely realistic either, because as you shift that about, you might be bringing in crappier and crappier units that are more likely to fail. So it could be that this is not a good assumption, that the variance gets larger as you expect more reserves, because more things can go wrong, possibly. But it's a reasonable approximation. Everything here is going to be so approximate, we can only hope for intuition. All right, yeah.
Would it have been fine if for P of G we used the probability density function of the distribution?
Well, there's a probability density function. Well, in the homework we made a Gaussian. I wanted to. You also, But what was your question?
We used the probability density function for the normal function.
Yeah, well, you took this to be a Gaussian in the homework, which is what this plot looks like. Yeah, that's right. Exactly. So yeah, in the homework, I wanted you just to play around with this on your own, and computation of this is not that easy. Optimization is much easier, which I didn't expect you to do. I just wanted you to play with it, in advance. But the point is this, that it looks like a convolution formula, and I've got a variable here which is my reserves, okay? And again, looking at this, if this was Gaussian, I've got a very, very smooth function of R bar, and I'm shifting around. It's a function of R bar for any G. It's very smooth. move it around, it's still going to be smooth. This is a beautifully smooth function of R bar. You know, smooth, differentiable. You know, it's going to be a happy face. It's going to be convex and smooth and everything. But then if you look at this other representation and move it, it's a convolution. So I can move through a change of variable, let u equals g minus R bar. I can make that, you know, call that u. I just made a change of variables. And put the R bar over here. Now this is piecewise linear, so it's not at all obvious now that it's a smooth function of R bar. But I convinced you here, and I haven't changed anything. It's the same function, you know. And this is a beautiful function to play with if you want to optimize. Isn't it? So you should have seen something like this if you did the homework. I know a lot of you didn't.
Tried.
Yeah. Okay. But you know, it's not that bad. But anyway, you should have got something like this, because basically what you're doing is you're smoothing. You start out with a piecewise linear function, and you're smoothing it out. It's like you're making, you know, you're adding some noise, and so you're making it smooth. And
So are we just allowed to assume that when we have a smooth function like a Gaussian distribution, that we're going to get a graph that looks like that?
Oh no, I mean, I'm using a lot of structure here. I'm using the fact that I know that that this is a convex function of R bar for any g.
Right.
You know, and I know that if I look at a linear combination of convex functions, I'll get a convex function. So I do know it's convex right off the bat.
Okay. So,
Okay.
you have to realize that if you multiply a convex solution with another convex solution.
Or not solution, but there's an integral. But think of it as a sum. If you take a linear combination with positive entries of convex functions, you'll get a convex function. Yeah, I mean, I didn't expect you to know that for the homework or anything. It's just something, it's a nice fact. And then here, I can convince you all that this is a nice differentiable function of R bar. Just been looking at this. It's true. It would take some proof, but you could show it. This is differentiable. So it's not, even though the original cost function has a corner, this with a Gaussian, say, will not have a corner. It's going to be beautifully smooth. And the reason I emphasize that is then I can take derivatives. You know, so I'm always screaming at you for taking derivatives when you are not allowed to. Well, here you're allowed to. So we know that at R bar star, the derivative is 0. You know, and again, I didn't expect you the homework. I wanted you to get you ready before this lecture. Now the thing is here, this is piecewise linear, you know, and if I differentiate this, you have to let me take the derivative inside the integral, and you can justify it usually, and we can justify it here. And what is it? So I'm taking the derivative inside. It's c of g minus blah, 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 blah. And then just, and that's p of g, right? And, oh God, is there a typo in that slide? Wait. Oh my God. There's a, I just found a typo in my slide. You see, it's when g equals d naught, this should be minimized. Oh, we are plotting versus G. Oh, I'm sorry, that is right. That is right. That is right. Okay, never mind. It's just how you write this is really delicate. Yeah, I guess sleep early. That's right. So, all right, yeah, no kidding. Well, I mean, it was a red eye, left at 2 a.m. this time, and landed at 9. So, yeah.
You just canceled class.
I say, yeah.
Postpone the exam.
No, all right. Anyway, so C of 0 equals 0, right? Yeah, C of 0 equals 0. Good. So it's when this is equal to 0 that things change. All right. So how do I put this in? So there are two cases. If this is what's the derivative if this is negative? If this is negative, what's the derivative? Yeah.
Easier.
It's minus the value of lost load. If this is negative. Yeah. And so it's minus the value of lost load if G minus D naught plus R bar is less than 0, and it's the other slope if it's positive. All right? And it's not defined at, when this is 0. That's just one little point, and that's not going to worry us. Okay, so we can justify that. All right, so that's what's really cool is that this becomes just a constant, and you have to integrate over two regions. You integrate over the region where this is negative, and then the region where it's positive. So it's equal to, let's just give it a name. And this I'll have to explain. What is rho? Well, you can tell what rho is. It's the integral from minus infinity until the first time this thing hits 0. And it's up until when G is equal to D naught minus R bar, right? When this thing first hits 0, it's when G is equal to D0 minus R bar. Okay. And then I'm also integrating upwards. So when integrating over G for which this is positive, it's just that. This is integrating over all G for which, the argument of the cost function was positive. All right? All right, again, when this is 0, that's the critical point. And that's when G equals D naught minus R bar. Okay? And when G is bigger than that, this thing's positive, the slope is plus CR. When this thing is negative, so G is less than that critical value, we get this negative constant. And it's 1 minus rho because the total integral, it's a probability density. The total integral is 1. So this has to be 1 minus this because the total integral is 1. Yeah.
You also accumulate that.
What's that? Well, no, rho is at one particular value, I think that's distracting to call it that because it's a function of R bar. I think it has a much more important interpretation than that. You're right. It could be interpreted as a cumulative, a distribution function. But no. It has a power systems interpretation. What is this? It's the integral over which this is negative is precisely the probability of not serving the load, the probability of lost load for a given value of R bar. Yeah, that's what's really crucial. So rho equals the probability of lost load. Okay, so of course it depends on our bar, but we choose it so we get this quality equal to 0. And so we can actually solve this. 0 is equal to that, and we get a formula. Oh no! What? Tell me! Stop! Why?
It's just like a lot of variables just like get thrown on the board.
Oh, okay. No. Tell me.
That's okay. I'm
Yeah.
so far.
No. That's it. We're done. So no, because look at the steps. I mean, it's just like, we've got a piecewise linear function. That's what's so nice. So the derivative becomes trivial, and we just have to interpret what it means then. So we have one. This is just the rho represents one range of integration, and the 1 minus rho is the remainder. And
C is C, the constant.
there's a CR here, which is the cost of reserves.
But C, which is multiplied by the whole G minus D naught.
Where?
So this is function twice y.
Yeah. This is the whole argument we went through. It's right through there. Yeah. Okay. And so you've got this as 0, and so you get a very pretty formula, right? Shall we do it? Luckily, there are 2 minus signs there. There's a CR there. The whole thing's 0. And so you guys do the algebra. So setting this equal to 0. So 0 equals this, equals this, equals this, equals this. When you set this equal to 0, I see a minus rho, which I can bring over to the other side, which is multiplied by a value of lost load and a CR. Bring the negative parts to the left-hand side and divide. And I'm going to get a CR over here on the right-hand side. And then the sum on the bottom. There you have it. Okay. So what's sort of fun here is what you start off with an optimization problem, and in the end you end up defining the target probability that you'd like. Because if rho star is exactly a probability of lost load, this just gives you a way to define the target.
I'm sorry, how did you get that again?
Oh, just the algebra. I'm saying you do the algebra.
Oh, you do.
I've got a linear function of rho, which I'm setting equal to 0. And you get this formula, and it is less than 1, It's a ratio, something positive over something bigger. Okay, so that becomes the target, and it gives you a way to think about how to define a target, based on cost. All right. Yeah.
So you don't even have to take a derivative of anything. You don't have to take integration of anything.
Yeah, you don't have to do any work. So that's the thing. If we didn't make this piecewise linear, we couldn't solve it. Yeah. I mean, what's that?
It would have helped if we knew this yesterday.
No, I didn't want you to solve anything. No.
No, I'm saying like-
This is not the homework. I didn't want you to do any of this. I just wanted you to plot it.
Right, but just understanding this in general.
Oh, no, I didn't expect you to take derivatives. No.
Okay.
No.
Then I have no idea what I was doing.
No. I wanted you to numerically integrate this for a grid of R bars and plot it. Yeah, just so you'd be thinking in advance before the lecture. That's all. Yeah. What's that?
You just can't hang.
Oh, you can hang. Anyway, did anyone plot it? You did?
But yeah,
Did you get it? Did you get a happy face like this?
it was very steep and then not very steep.
Yeah, good. Yeah, I made this because of the numbers here are so extreme.
Where were you yesterday?
Yeah. Because the cost function's so extreme. You get that. Okay, so anyway, so again, the conclusion is right there. Minimizing expected cost is equivalent to, coming up with a target in that way. And all right. Now, all right. So happy, reasonably. Yeah.
For the homework, I solved for the
Yeah. Well, I didn't want you to, but I wanted you just to see numerically. Yeah.
But I think I found a source somewhere on how to do it for a normal distribution using z-tables. And no, it looked similar to the rose stuff. I don't know what that symbol is, but the thing you have off.
Well, here,
Yeah.
so rho, we have to solve this, and that's something you can't do because if this is Gaussian, this is now we can use this insight that this is a cumulative distribution function for Gaussian, which doesn't have a closed form solution, So you'd have to numerically invert this to get R bar, So you have to solve this equation to get the optimal R bar, and that doesn't have a closed form solution. You'd have to get it from a table. And MATLAB will let you do it. MATLAB will do it numerically for you. But again, I didn't expect you to do that. Is that clear? Or okay, all right.
I still want to know, what is R bar star like?
No, right, that's what I was saying. Rho is a function of R bar. Okay? And so once I know what the best rho is, I have to invert this equation to find R bar. So once I know rho, I know R bar. But unfortunately, for Gaussian, this is an invertible. So you can't, we don't have a closed form expression for it. MATLAB will do it numerically for us, but yeah. And you'll get something that's very insensitive to these values, it turns out. It won't be, the exact values of CR and so forth aren't going to be that important. Now, just like with economics, this is really extremely naive, and it's too complex to do any better. Because think about what actually happens in practice. I can kill this now, right? Death. So this is all standard textbook stuff, and it is the way people talk about these things in control rooms. Bob Moy, who's been in this industry for 30 years, is going to attest to that. He'll give a talk at some point. But think about what happens in practice. Is that, you've got, one day, and you've got the actual demand, is just too complex, and they're aware of that, and so it's a hack in the end. So this is good for intuition, but I have no faith in any meaning, that this really is an expected cost in a real sense. It's great for intuition, but this is the kind of thing that's way too hard to get good enough models to have much confidence. So it's a hack. Anyone tells you any otherwise, just, I don't know, walk away, because it's a hack. There's no way. The 12% reserves in Texas, or actually they don't mandate in Texas, but in some places, is really just fooling around with this and then finally saying, to hell with it. You said 11%, let's call it 12. All right.
You say, like, if we can ever get to a point where the planned reserves are super close to the actual demand?
Well, it happens. It's absolute panic. Yeah, I mean, when this really gets low, if it goes to 5% instead of 12, they have scarcity pricing in parts of the country, especially in Texas. So as prices go to $9,000 a megawatt hour, that's scarcity pricing. They just make the price shoot up when this gets low. And the closer this gets to zero, the more they make those prices go up. And it'll hit that $9,000 ceiling. And PJM, California ISO, they're all into this scarcity pricing to make the prices shoot up to massive values whenever this gets small. Why? It's just, I mean, it's nuts, I think. Because why would you do it? I mean, why would you increase the price in an emergency? It doesn't, you know what I mean? It's sort of like, let's not pay firefighters anything, but when there's a fire, we'll give them a lot of money. And you think about what that would mean. You would incentivize firefighters to cause fires, and would it create a more reliable workforce? Would you be sure of having a lot of firefighters available by having a payment scheme of that form? It's sort of, I don't think so. So it's so I'm really fighting this. I think the scarcity pricing idea is a terrible way to go. But yeah.
The scarcity pricing is not it's a solution of the optimization.
Well, no, it's a hack. It's not. There's no real.
I thought that because demand plus reserves, then the scarcity pricing would be a solution.
No, I mean, if you actually did this, so we could apply our competitive equilibrium theory that we developed over the last weeks, and we could apply it to the problem with reserves. And remember how price is marginal value? Well, what's the marginal value of reserves to you? What would you pay for a little extra reserves? Zero. Zero. So if you actually worked out the perfect competitive equilibrium model for this, you'd get zero prices all the time whenever the reserves were positive, and they would hit marginal value when the reserves became negative. This horrible number, that $20,000 that I've been making fun of. And that's known to some of the power economists. And so they're trying to mimic that ideal behavior. It's not politically feasible to do that, so they're trying to mimic something like it. But that ideal competitive equilibrium is based on assumptions that don't make sense anyway. I mean, right? I mean, all the assumptions we had to put in place to justify competitive equilibrium. No, it doesn't. To me, it doesn't make sense on economic grounds, and I know it doesn't make sense in terms of long-term incentives. If I'm only going to get paid when there's a crisis, then it's going to have to be a lot of crises if I'm going to get into the business, right? I'm not going to get a loan to, purchase equipment if my business is that risky. I'll have to make sure there's a lot of crises. So yeah, but yeah, so it's tough. Yeah. So I want to take a break a little bit early. I'm tired. So especially we're going to go into a quick overview of a different topic. So let's take a break. And yeah.
Can we also go over just logistics for Tuesday?
Yeah, absolutely. So yeah, absolutely. And why? Yeah. No, all of that stuff.
Number 1 to 4.
Yeah.
Sit it under the table.
Yeah. But I will prepare a handout, and yeah. Yeah, and there'll be office hours Monday and Tuesday, and yeah, and I've got the,
Class two.
and we've got class as well, but
I
yeah.
won't be here.
You won't be here? No.
I emailed you.
Oh yeah, okay. Yeah.
Tomorrow we'll have class or maybe next week?
What's that? No, there's an exam on Tuesday, and so I'll have office hours next Monday and
There
Tuesday.
will be no class.
Oh, there will be. Oh yeah. Oh yeah. Well, I'm sure.
So the exam is not on class time.
No, it's in the evening. Yeah,
Evening.
yeah. The two midterms are both in the evening. So,
The cheat sheet, you mentioned 3
Yeah.
minutes. Is A4?
oh yeah, oh, sure. I mean, just yeah, standard paper. Yeah.
2 is fine.
I mean, well, one page double-sided on the first exam and two on the second. Yeah, and yeah, and double-sided, and yeah, and you can't bring a magnifying glass. Not really. So here's the thing. Okay, so we do need to know a little bit about volatility, and and what it means, and 2 hours is all the time. 2 or 3 hours is all the time we have for that. So that's all the probability you'll see in this course. And I might use some of that. This idea that you can represent a random process as a sum of sinusoids, it's really useful for intuition. And it's just a generalization of Fourier series. That's all it is. Fourier series allows you to decompose a signal in terms of sinusoids. There's a generalization for random processes. That's useful for intuition. This monster, we need to understand that a power network is not the same as a communication network, and it has really exotic dynamics and really hard to understand, and nobody understands them. Even experts in the field, don't understand the whole system. Everyone understands a little piece of the system, but there's nobody who has a global perspective, especially not me. And Illinois was the best place in the country for power. Pete Sauer is amazing, but he's the first to admit 10%. It's just a difficult field. So I mean, we're not going to go through all that, but we do need to understand why the role of big generators today in stabilizing the grid, and that's not going to go away for a long time. Those big monsters, I mean, FPNL just invested, $4 billion in power generators. They're not going to walk away. Those are going to be running for that, a half a century. And these massive coal generators in Michigan, they're going to be there for quite a while. And hopefully we'll find better ways to deal with coal. So I am going to talk a bit today about the dynamics of these big, massive generators, and then next week on governor control and how that shapes the dynamics of the whole grid. And once we have that in place, we can get a better feeling of how we can apply some crazy ideas. Like how we would use batteries to regulate the grid, things like that. So, but we definitely need this. So we don't have some intuition about the dynamics of generators and how they contribute to the dynamics of the grid, we're dead. All right? And okay, so let's go through this slowly. So all I'm going to talk about is this part of the picture. This big monster steam turbine generator. Okay. So there's something here that feeds in fuel. It might be coal, or it might be natural gas. Not wind power, not solar power. So I'm talking about big, heavy monster machines. All right. This is hundreds of megawatts, creating horrible smoke. Probably, I don't know. And then there's a generator here. And let's go figure this out. So the turbine takes in fuel like natural gas and creates mechanical torque on a shaft. And this generator takes that mechanical torque and creates power, but also back EMF. There's a torque because of because there's a motor here. A generator is also a motor. And so this is what things look like. If you go Google these things online, you'll find pictures like this, which is what I did. And that looks like a scary nuclear power plant, but it also could be a coal plant. I mean, cooling towers are common to many big generators. And then you've got all the craziness here, these very complicated generators. And I want to say something right here. So we're going to be talking about keeping the frequency at exactly 60 hertz, well, not here actually, but well, actually the picture isn't here, but we're going to be trying to keep the frequency in the United States to 59.5 hertz is okay, or 60.05 hertz is okay. And last year I taught this course, I wanted to find one source that would tell me why. I've heard this all my life. I know there's issues of the fact that power systems are very nonlinear, and if you go outside of a linear region, you know nothing. But that's way outside. And that would be why 59.5 hertz? Below that, you start to panic. Why? And I don't know. I wrote to my colleagues at Illinois and I said, I hate you guys. Because I was reading Tom Overby, who's at Illinois, his book. He said the world will end if the frequency goes below 59.5. Every book said this, that the world will end if the frequency goes below, 1/2 of 1 hertz. And finally, I got an answer, but I laughed. I thought it was ridiculous. So it looks like, do you have an answer?
Well,
yeah.
Sort of.
Yeah.
You're going to talk about the inertia from these moving machines kind of keeping the frequency stable.
Yeah.
And when you go so far off the map, it's only half a hertz.
Yeah.
I mean, once you get to that point, it's almost like the point of no return. You're going to get these frequency spasms.
It can happen. I mean, you think about it. You've got a bunch of. I'll show you some simulations next week to show this. You've got these generators. They're coupled to electricity, torque, and it's almost like they're on the same shaft. And so if they're different frequencies, it's like the shaft will break. It's almost like that. But that's a really coarse thing. I mean, in India and in Europe, they let the frequency go around a lot more than in the U.S. And in India, it's all over the place. And it doesn't, there are blackouts, but it's not so much that. So there's another reason, which is amazing, which almost nobody, even power engineers don't know, is that the really high efficient monster generators have all these fins in the turbines. And they're, these blades that have a resonant frequency, And to make them really efficient, they tend to have a resonant frequency which is close to some multiple of 60 hertz. And you've got a huge population, 100, 200 generators, and everyone has a different resonant frequency. But you just only have to excite one of them, and that generator will kick itself out of the system, and automatically. So it's not going to wait for that oscillation to happen. As soon as the frequency sags, it's been designed so it'll just shut out because of fear of resonance inside. And so Joe Chow at RPI has references there, but it's not in any books. And that's what GE says as well. But it's actually resonances inside these monster generators, and the super high efficient generators are very fragile in that sense, that they can break. And the monster, that's why, and they don't have as many of these super expensive high efficient generators in Europe or in India, and they're more robust to that. So it's so what you said is absolutely correct, But this incredibly stringent, like 59.5, is actually something about the single generators. It's amazing. Yeah. What's that? Yeah. Yeah. 2 millihertz. Right. 2 not 2 millihertz. Well, I'll come back to that. We'll come back. Okay. Because okay. So how do we get? So again, this isn't going to be on any exam. I just want us to get some, and parts of it will, but not all this crap. So I just want you to know that there are generators that have a stator and they have a turbine and all of that, and you can pick them apart. And the number of pole pairs. This is the case with the 2 pole pairs. So, the motors inside determines the rotational speed. So if this is a single pole pair, the speed of this will be 60 hertz. But these big monsters don't want to run there, so you have a lot of poles, so they can run slower to keep at 60 hertz. So that's it. So it really is. I mean, it's a physical object that really is spinning to maintain that 60 hertz. It really is. It's not the computer scientists take everything else. They can't take this. This is a physical device. You know what I mean? It's not an algorithm. It's really spinning. And then you get, F equals ma. Ma equals F, because you put it right the other way. You basically have, A here is angular acceleration, and J is a moment of inertia. And there, again, like as I said, there are two torques on this shaft. And one is the mechanical torque from the turbine, and then there's this back EMF, there's an electromechanical torque from the generator. And there's that difference. Now, that's not really what we want. Torque isn't something that we're not most of us aren't mechanical engineers. We don't care about torque. And we care about power in all its forms. And so, I should say again, so this is a function of fuel, and this will depend on load. The torque will disappear if there's no load, which is scary. So if the load suddenly disappears, that disappears, wham, this thing's going to accelerate and trip. You're going to have a problem. But so basically what you do is so torque is force, and energy is force times distance. So power should be force times speed. Okay? And so you have to multiply both sides by speed to get power on the right-hand side. Yeah? So multiply both sides by speed, and that's what you get. All right, so going from here to here, I'll go back and forth. I don't want to make you too sick. All I can do is multiply both sides by the speed of rotation, because torque times speed is power. And so the J turns into M, which is just going to be speed times J. And I've got mechanical power due to the fuel, and I've got this power due to the load basically, electrical power there. Mechanical power and electrical power, which is going to the loads. But I forgot, but I stuck in this crazy thing here, which is often done. What's that? It's gobbledygook. It's a fixed factor. So the stamping constant is just thrown in to represent some things that we can't model very accurately. There might be loads, might be other things. Okay, so you'll see that very often. All right. So that's a dynamical system, and it looks easy. Big deal. It's a beautiful linear system. What's the big deal? That's the thing. Anybody coming into this as a controls person would say, geez, what could be more trivial? It's not a communication network, but it's not much harder. Wouldn't you say that? But Kirchhoff's laws come to kill us. That's the trouble. Yeah, Kirchhoff's laws are enemies here. So anyway, that's the swing equations. So I guess I will make you memorize that make you put it on your cheat sheet for exam 2 in December, because I'm not going to expect you to know this now. But here's an example, which I'm not going to go into too much detail, just to show you how little things can become awful. So it's a pretty contrived example, because I've got what's called infinite bus here. I've got a constant voltage here, and this will absorb or take any power we put into it. And I've got a strange, I've got just a capacitor here, which is a bit odd. It's just to come up with a simple example for illustration. If I could have a different impedance here, and we get different dynamics. All right? And this is meant to be underlined. If you click this, you'll get a really nice tutorial, which is where I stole some of these slides. So Ian Hiskins at Michigan came here and gave a few tutorials a few years ago, and you can see. I'll give you links to videos and some of his slides, which are pretty good. But so you write down the swing equations, and you have to remember your phasors. And I don't want to review phasors. I might be forced to a little bit later on. But if you plug along and look at a phasor analysis of this, what you get from the swing equations is you're going to get, when you work out what the current is across this line, and write down the formula for power, there's going to be a Pmax, which is the product of these voltages, the voltage here at the source here, and a voltage here at the load. It'll be a product of the two voltages divided by x, this multiplier here. And you get that just by playing around with, oh, I don't want to write it down even. Well, that's S. Forget it. I'm not going to do it. Later on, when it really is relevant, I might review some of this stuff. But go back and look at your phasor analysis that you should have done. And I actually panicked at first, thinking there should be differences, but it really does come out to this if you do the algebra. Now, that's not a very pretty system. So we start out with something wonderfully linear. You know, it's just the fantastic, simple linear differential equation. And just because of the awful way in which phasors work, the real power here is a function, you know, of this theta value. And oh yeah, I should have said this very loudly. These are all deviations now. When you write down the swing equations, they're always, you assume they're deviations. And that's partly because you end up with nonlinearities like this, and we want to linearize around the nominal value. So omega here is not 60 hertz when you look at the swing equation. It's the difference, the actual frequency minus 60 hertz. So 0 is a good thing. It means that you're, all right. So what this is it's really what a nonlinear pendulum would look like. If you actually modeled a real pendulum, it would be just like this. And only it's worse in a way, you know, because pendulums, I don't know, if they go up, they'll come back down, you know, and this could possibly not. You know. So it's got an equilibrium. So this is a state space model. And all of you checked off you knew nothing about control, so I guess that's too bad. By state space model, I mean if I take the vector theta and omega together, and I look at the derivative, that's some function of itself. And well, I've got these other inputs as well. There we go. So it's a controlled state space model. So the derivative state, vector derivative, is some function of the state and this input, because the mechanical torque is something I can adjust through fuel, by pumping down the fuel. Yeah, so this is something we will be spending a lot of time talking about. So right now, we're going to talk about, first of all, how it's done today. And, there's this governor response that kicks in. There's what do you think controls this rate of change down here? The fact that there's a certain slope here. This is, what's the range here? This is 10 minutes. So it takes a minute or so for this to happen. Yeah. And it's just the whole, this is Midwest Idaho, it's filled with massive numbers of, hundreds of these massive coal generators. And so the collective inertia is huge. And so that slows down the rate of change. That prevents the frequency from dropping too quickly. That's one layer, is just inertia of the grid. And which is disappearing. So there's a real concern about that. In places where they're replacing a lot of traditional generation with wind, they're concerned about that lack of inertia. So the slope here could be steeper depending on how we design the grid. After that, so after the inertia, there's actually governor response, which we'll be talking about. And then this is something completely different. This restoration is layers and layers of control. So initially there's local, completely distributed control. There's the natural behavior of the system, inertia, and there's local governors that look at local measurements and do things. And then you have more of a centralized control architecture that brings things back up. And we really need to understand that well to think about how we can do things better, and how to save California and Texas from, so that they can deal with all these renewables. And so that, there it is. So I didn't even realize that was it. So I can't really go on because we'd be getting to governors. The natural next point would be to talk a bit about architecture of governors, but you've seen that. You all know what a governor is. It's just, I will say a few things though. I will say a few things. What's really fun about this, when we get to this, is that, a governor is an obvious thing. You've all seen pictures of the Watt governor with the weights. It spins around. If it's spinning too fast, the weights go up. If it spins too slow, the weights go down. And that regulates speed. Well, of course, this has a computer. It's not doing that. But what's beautiful is it's actually a kind of a cool local control architecture. It's not trying to bring the frequency immediately back up to 60 hertz. It's doing something much more subtle. And we need to understand that pretty well. And it's a big issue today, how to design this in a robust way. It's not, it was completely a settled science when the grid was sort of in steady state with primarily massive generators. But when you bring more and more renewables in, you have to rethink about how you should set these the parameters in these governors, and maybe just rethink them altogether. So that's what's fun. Is a lot of research questions here, and really dangerous ground. This rate of speed is where you could really blow up the grid, and if you don't do things right, And that really, the last few years, there's been a lot of concern about that.
Geothermal and all won't have power.
What's that?
Geothermal.
Yeah, all these things. Yeah, so that's the thing. So it's a curse that, well, forget geothermal. It's such a small part, but that wind and solar don't have any inertia. But it's a blessing that they have all these power electronics to do something. But on the other hand, you can't make inertia from power electronics. Inertia is some sort of storage, and you can't do that through an algorithm, and you can't do it through just power electronics alone. You're going to have something like storage, if you're going to have something mimicking governor response. And so that's all new. In a way, it's a big research area to do that right. And so it'll be interesting to look at how it's been done historically and how we might think about doing it in the future. So that'll be over the next weeks. But I'm here. It's a short lecture, I guess. But if anybody has any questions, I'm here to answer them. About the exam, I'll get a handout prepared by midnight tonight. Office hours Monday and Tuesday. I'll let you know. Yeah.
And so you have office hours on Tuesday after class as well?
I think I'll do it maybe before class. Maybe I'll see. Should maybe is after class better? Maybe it is. Maybe sometime in Monday. Maybe after class. That seems awfully late. I was thinking the morning.